So we're going to be talking about graph databases for Python users, and this is going to focus on the data science side of things. So Neo4j classically is used to power applications, but it can also be used as a tool in data science, where you use it to store your data for whichever data science project you might be working on. So this is our agenda for today. I've put together some Jupyter notebooks, formerly IPython notebooks, to go through all the different ways that you can integrate more analytic type packages within Python with Neo4j. And so this webinar assumes you already know what Neo4j is. You've already watched the intro to Neo4j videos. And so we will be just jumping right into Python with Neo4j. So if you don't know what Neo4j is, I suggest you pause this video now and go watch one of those. But anyway, we'll be looking at a Hello World notebook where we just go over some really basic code examples to get various packages integrated with Neo4j. We'll first look at Py2Neo, which is one of Neo4j's Python drivers. And then we'll look at IPython Cypher, which is a really cool package that allows you to easily query Neo4j from your IPython notebook, now Jupyter notebook, and it'll coerce your Cypher query results either to Pandas data frames or to NetworkX Graph objects, so we'll look at that. Then we'll look at iGraph, which is a graph algorithms library within Python. It exists in both R and Python, but obviously we'll be looking at the Python side of things today. And then there's this graph 3D package that will allow you to visualize your graph in 3D, which is pretty fun, so I want to go over that. And then we will look at an example project where we take the code that we just looked at in the Hello World examples and actually apply it to something real. And that will include importing the data, making some charts, some graph algorithms, and some graph visualizations, and that's all around a Twitter data set that I've imported into Neo4j. So if you do want to follow along locally, or you want to be able to view this stuff in your own browser, you can go to this URL right here. This will be sent out later, so don't fret if you miss it. nicolewhite.github.io/neo4j-jupyter/main.html will bring you to this page, and then clicking on these links will take you to the respective notebooks. Anyway, I have some slides. These notebooks have been converted to slides, so I'm going to go through these. So we're going to start with Py2Neo. So like I said, Py2Neo is one of Neo4j's Python drivers, and it's a full API around the Neo4j REST API and more. And of course, it'll let you do low-level things like creating nodes and relationships and retrieving them individually, and then of course it'll allow you to do Cypher queries. So let's figure out how we connect to Neo4j from Py2Neo. So from Py2Neo, you have to import the graph object, as that is going to allow you to connect to Neo4j. And here for safe measure, I'm deleting everything in my graph to make sure it's empty. So use that with caution. That will delete all of your nodes and relationships when you call delete all. And then this right here, this scripts viz import draw, that's just something I wrote in the background for the purposes of visualizing what we have going on. That can be studied on your own time when you get a link to the GitHub repository. But anyway, the main point here is that you connect to the graph with graph equals graph. Then you can create nodes with the node class. So from Py2Neo, import node. And then the syntax here is node, and then the first argument is the node label. So here I'm saying I want it to be a person type node. And then anything after that is an arbitrary amount of key value pairs. So here I'm saying I want the name property to be Nicole, and I want the age property to be 24. Then I have this other node, also a person node with a different name and a different age. And then I'm creating a few different types of nodes here, a few different node labels. We have persons, we have drinks, and we have manufacturers. and they all have some amount of properties on them. And then we're passing all of those to graph.create. So simply executing these lines up here don't actually create the nodes. You have to pass them to the create method on the graph object, the graph variable. So we're passing all of those to graph.create. This options dictionary is just something I have to use with my draw function. And here we see all of the nodes that we've created in our database down here. So the red nodes are drink nodes, the yellow nodes are, manufacturer nodes, and the yellow nodes are drink nodes, and then the blue nodes are person nodes. And then we're displaying the name property down here, but if you hover over, you should be able to see all the other properties on those nodes. So that is our current graph structure, but as you know, graph databases aren't terribly exciting if you don't have any relationships. So you should probably add some of those. So syntax here is going to be pretty straightforward. We're going to import the relationship from Py2Neo, and then we can create relationships by passing the from node first, so the source node or the from node, the relationship type, and then the to node or the target node. So here we're saying Nicole likes Coke Zero, Nicole likes Mountain Dew, Drew likes Mountain Dew. And then all of these are, of course, referring to the nodes that we just created and assigned to variables in the previous code snippet. And so here we're just creating a handful of relations. Now, if we draw a graph again, our nodes are actually connected by relationships at this point with different types. So we see that Pepsi makes Mountain Dew, and Drew and Nicole like Mountain Dew. So that is my Hello World example for Py2Neo for creating nodes and relationships in Neo4j. And of course, Py2Neo supports retrieving Cypher query results. This is probably the most standard way or conventional way to interact or read data from Neo4j is to write a Cypher query. So in Py2Neo, makes it very easy. You write a query as a string. Here I'm matching on all person nodes that have an outgoing likes relationship to a drink node, and then returning the name of the person and then the name of the drink. So here we're just getting a table with 2 columns, 3 rows, because Nicole likes Mountain Dew and Coke Zero, and Drew likes Mountain Dew. So here we're getting a tabular results into Python via graph Cypher executes, where the syntax here is the first thing you pass is the query itself, and then we'll see later what other arguments might be to graph Cypher execute. And this returns to you a record list where each element is a record, but you can essentially treat it as a list of named tuples, which we'll see in a few seconds how you can access the actual values in this table. So we can see that rows can be accessed by index, so the first row is data 0. And then columns can be accessed by key or attribute. So if we were to iterate through each row in this record list, we could access the columns either by key, like so. So here we're accessing the name column by key, or by attribute. So here we're accessing the drink column with row dot drink. So we're accessing the drink column by attribute. So that's the 101 on how to deal with these Cypher query results, Py2Neo Cypher query results in Python. We should also look at parameterized Cypher, which is where you have a parameter that you want to fill in later. So here we're matching on person nodes that have outgoing likes relationship to a drink node. So same thing there in the match clause, but we're saying that it has to be a particular person node where the name property on that person node has to be some parameter that we're going to pass in later. So in Cypher, parameters are wrapped in curly braces and they're named. So you have to name the parameter. Here the name of the parameter is name. So this is like in SQL when you have the question marks that you want to fill in. later, Cypher, we call them name parameters, and they're wrapped in curly braces like this. And this query parameter name to be passed in. So then we're returning the name of the person and the average calories of all the drinks that they like. So here we're filling in the name parameter with Nicole. So here we're using graph Cypher execute again, where the first argument is necessarily the query, and then any arguments after that should fill in any parameters that the query expects. So here we're saying the name is Nicole. And so this is important if you end up building anything like maybe a dashboard or what have you with Python and Neo4j on the back end, you might use our inputs that you want to pass to a Cypher query, such as if they select things from a drop-down list and that is needed in the Cypher query, then you'd want to pass it in as a parameter to avoid injection attacks and stuff like that. IPython Cypher, so as I said before, this is meant to be used with IPython notebooks or Twitter notebooks, and it'll make writing Cypher queries and getting those results back very, very easy. So let's look at that. So after you pip install IPython Cypher, you can load the Cypher magic like so. And then you have two options available. You have Cypher with 1%, which is intended for one-line Cypher queries, and then the Cypher with double percent is intended for multi-line Cypher queries. So in IPython, if you place the double percent Cypher above a multi-line Cypher query, it'll display it in a table below, like so. So here we're matching on persons liking drinks, returning the name of the person, the name of the drink, and then the calories of the drink. So if you use IPython Cypher within a notebook, you'll be able to get these nice tables without having to, if you were using Python, you'd have to write the query as a string, you'd have to pass it to graph Cypher execute. Whereas this will just let you have the bare Cypher query and get a table below, which is nice. It's also nice because it will coerce your results into a Pandas data frame, which if you're more on the data science side of things in Python, you are very familiar with. So we can do that with the, we use the single percent Cypher at this point because we want to assign it to a variable. So here we're assigning the Cypher query results to this variable called results. And at this point, we have to separate our query with these backslashes if we want to have multiple lines. So same query here, matching person liking drink, returning the name of the person, the name of the drink. And then we are getting we're getting that into a Pandas data frame by calling getDataFrame on this results variable. And now we have a Pandas data frame. And notice that we have the 0, 1, 2 here displayed because the Pandas data frames are all indexed, of course. So then you can, you can see the 0, 1, 2 are the indexes. You can access a certain row with ilocate. Here we're accessing the second row as indexing starts at 0. And then you can access columns by key. So here we're getting the name column. So everything you would expect from a Pandas data frame. You can also grab NetworkX Graphs out of Cypher query results with IPython Cypher. So of course you'll have to install NetworkX first with pip install, import it, and then you can assign entire paths to result sets. So here, instead of returning the actual properties in the previous results, we were getting a table of properties. We were returning the name of the person, the name of the drink. Here, we're returning the entire path as an entity. So here we're matching on person likes drink, and we're assigning the entire path to an identifier P, and then returning the P, and assigning that to a variable called results. Then we're calling getGraph on that, and G is now a NetworkX graph. And then we can pass that to draw, the draw method on NetworkX to get our graph in NetworkX. And then at that point, once it's in a NetworkX graph, you can do all of the NetworkX things like viewing the nodes. So we can see that it's retained all of the data that as it was J. So we still have the calories property on there. We have all the labels that are on the nodes. We have the name properties. So no data was really lost. It's just now in a NetworkX object, and you can run graph algorithms, for example, viewing the degree of each node. So that is a simple code example of how to grab things from your data set, from your Neo4j database, and pull it into a NetworkX object in just a few lines of code using IPython Cypher. All right, iGraph, like I said, is a graph algorithms library. It's, I guess, an alternative to NetworkX. But if you do want to use iGraph, IPython Cypher doesn't have a method for converting a graph to iGraph, at least as far as I'm aware. And so I'll actually use Py2Neo to make this happen. So we have to import a graph object from both Py2Neo and iGraph, so you have to alias them as something different. And then we'll create a new graph object called Neo4j, write a query. And then we can get those query results with Cypher execute, which we've seen already. And the point here is that you want to return an edge list from Neo4j because iGraph will create graphs from edge lists. So here we're creating an edge list between people and drinks. And then this is just a subgraph from Neo4j. We still have our manufacturers in there as well, but we're grabbing a specific edge list that we're interested in pulling into iGraph here. So we're grabbing the person, the name of the drink, and then when I say edge list, that means each row indicates that this node is connected to that node. So Nicole is connected to Mountain Dew, Nicole is connected to Coke Zero. That is what I mean by edge list. Then at that point, you can just pass that straight to iGraph's tuple list method to coerce that into an iGraph object. So we could take the raw results from Py2Neo, this data variable, and pass it to iGraph's tuple list to get the iGraph graphed object. And then, of course, at that point, once you have it in iGraph, you can run all the iGraph algorithms that exist. So here we're finding the nodes with the maximum degree. And finally, we have this Graph 3D library, which confusingly is also called iGraph, at least on GitHub, but I renamed it because otherwise you would have conflicts with the other iGraph. But anyway, this will allow you to draw 3D graphs and manipulate them with your mouse. And the syntax here is pretty simple. It's a list of tuples with source and target nodes. So node 1 is connected to node 2, node 2 is connected to node 3, so on and so forth, to create a graph like so. So that's just, those are just random numbers, but more realistically, you'd want to pull out data from Neo4j and visualize it with this Graph 3D library. So here, I'm matching on all nodes that have a relationship, returning their IDs. So that's returning an edge list of all the nodes in our database, and then they need to be a proper tuple, so iterating through that to get a tuple for each element, and then passing it to Graph 3D Draw, and that will give you a nice 3D graph of what you have in your database. So that's the end of my Hello World examples. So let's actually now jump into the example project, where we'll actually apply this stuff to something a bit more realistic. So, I think I mentioned this earlier, but I have some Twitter data in Neo4j. I have a script that imported various tweets over a few hours. I'm not going to go over the import script because it's pretty unexciting. It's just dealing with the Twitter API for the most part. But you can certainly study it on your own time when you get a link to the GitHub repository. And then I collected tweets that have the words Python, rstats, or Neo4j, and imported them into Neo4j. And these were collected over just a few hours the other day. So this code is, we're just getting an idea of what our model looks like at this point. So here we have that we have tweets, hashtags, and users. So here we have Node.js and PHP. These are hashtag nodes. All the red nodes are hashtags. And they have outgoing tags relationships to tweet nodes. The blue nodes are tweets, and they have a text property with the text of the tweet. And then the hashtag property has a name property of the name of the hashtag. And then we have users. So users post tweets, and then tweets can retweet other tweets, as we see here, and tweets can mention other users. So we only have 3 node types, but then we have a handful of different relationship types, where we have hashtags tagging tweets, tweets retweeting other tweets, users posting tweets, tweets mentioning other users. And then not shown here, but it is also in the data set, I don't think it's in here, is tweets can also reply to other tweets. So a pretty graphy data set where Neo4j is pretty necessary for modeling and querying this very highly connected data. So that is our model in a nutshell: tweets, users, and hashtags. And let's create some plots. So I have been using Plotly lately. So we're going to make some charts to get some really basic insights about what's going on in our graph. So we're actually going to use IPython Cypher in this set of code snippets, because it'll let us, as we learned earlier, we'll get some Pandas data frames, and then it's trivial to pass those to Plotly and create some charts. Here we're importing the Plotly stuff that we need. And if we want to answer a really simple question, what are the top hashtags, and we want to visualize that, we can write a Cypher query that will find the hashtags ordered by the number of tweets that they've tagged. So here we're using the same syntax that we saw earlier, where we're using the Cypher magic to write a query and assign it to a variable called result. So here we're matching on hashtags that tag tweets, and then returning the name of the hashtag and the count of how many tweets that the hashtag has tagged, ordering by that descending limiting 5. So we're getting the top 5 hashtags by usage in this data set. And then, as we learned earlier, we can call getDataFrame to get that into a Pandas data frame, and then df at this point is a Pandas data frame. And we can look at the top 5 rows. There's only 5 rows anyway, but this is our Pandas data frame. And so we see Python was used 271 times, machine learning 33, so on and so forth. Then at that point, very easy to create a bar chart in Plotly with this data. So saying that we have a bar chart where the x-axis is the hashtag and the y-axis is the count of tweets. And then at that point, you just pass it to Plotly, and it gives you this nice bar chart within IPython or Jupyter notebooks. Let's also look at the hashtag and mention distribution. So by that I mean, for each tweet, we want to see how many hashtags it has and how many mentions it has, and then we want to look at the distribution of these counts. So we're going to write a query where we match on all tweets, then we optionally match on hashtags in those tweets, and then optionally match again on tweets mentioning other users. And we're using optional match here because we want to get results, for example, where they don't have any hashtags or mentions. If I use optional match here, I wouldn't actually, this row number 4 wouldn't be here because the tweet didn't meet the criteria for the match clause. It would only have matched on tweets that do tag tweets and do have outgoing mentions relationships. And so we use optional match to still retain the tweets that don't have those relationships in the results set. So that tweet was still returned as 0 and 0, because then we're counting how many hashtags and then we're counting how many mentions that tweet has. So then I'm coercing that to a data frame, deleting the tweet ID column because we don't need it, and now we have this table of hashtags and mentions. So it had 1 hashtag and 5 mentions. This one had 0 hashtags and 1 mention. So this is a row for each tweet with a count of hashtags and mentions. And then we can create a histogram. I've decided to overlay it. And so here we have two histograms overlaid where the x-axis is the number of hashtags, the number of mentions, and then the y-axis is the frequency of how many of the tweets have that count of hashtags or mentions. And so we can see that the majority of tweets have no hashtags and no mentions. They have 0 hashtags and mentions. And then it's interesting that if it's going to have one thing, it's more likely to be a mention. So a lot of tweets have one mention where they mention one user. And then if you're going to use a hashtag, people tend to use a lot of them. So if there's anything that's going to be, in the frequencies to 6, 8, or 10, it's going to be hashtags. So people are more likely to use an obscene amount of hashtags than they are to use mentions. So it's unlikely that someone will mention, 6 to 8 people, but they might mention, or they might use, 6 to 8 hashtags. So that was interesting. And let's do some graph algorithms. So the typical workflow, I think I mentioned this earlier, is to retrieve a subgraph from Neo4j with Cypher, and then pull that into iGraph and do some analysis there. Of course, you could use NetworkX, so you could do the IPython Cypher to NetworkX integration that I showed earlier if you prefer NetworkX. I just happen to prefer iGraph, so we're going to do that instead. So we are going to grab some Cypher query results and pull that into iGraph. So let's say we're interested specifically in a subgraph of users mentioning other users, and we want to analyze this subgraph within iGraph. So here we would grab a Cypher query edge list and then put it into iGraph. So here we're matching on a user that has an outgoing post relationship to a tweet where this tweet mentions another user. Then we're returning the user1 username as the from node, the user2 username as the to node, and the count of how many times that's happened is the weight. So that's giving us an edge list, as I mentioned earlier. An edge list means that for any row, this node is connected to that node. And then this isn't necessary. I think I was doing some graph 3D. This is only necessary for the graph 3D stuff. I could have passed as is to the iGraph tuple list. And then we're saying that the weights are true because we have this weight column in the data set. And if true, then iGraph looks for a column called weight and assigns that as a weight to the edge. So in this iGraph subgraph, we have nodes that are all users, and 2 users are connected if they've ever mentioned each other. And then the weight on the edge is how many times that has happened. So then, once you have your subgraph pulled into iGraph, you now have the ability to run these, global graph algorithms that are pretty expensive. For example, the betweenness centrality is a pretty expensive operation because it is a count, it's a ratio of the number of shortest paths that pass through V divided by the total number of shortest paths in the entire graph. So the betweenness centrality for any node V is the number of shortest paths that pass through V out of any pair of in the graph, all combinations of pairs of nodes divided by the total number of shortest paths. So a pretty expensive operation, but iGraph makes it really easy. So here I'm grabbing the name of the node and then the betweenness centrality, which you can grab with the betweenness method in iGraph for each node in the vertices in iGraph. So this is just doing a list comprehension rather. For each node in the iGraph vertices space, give me the name and the betweenness as a tuple, and then I'm sorting it and giving us the top 5. So we see that Neo4j, someone dev topics or rather media have very high betweenness centrality in this subgraph of users mentioning other users. All right, let's switch gears. So let's say we're bored of this other subgraph that we were just dealing with, and we want to look at now a subgraph of hashtags mutually tagging tweets. So we'd write a new query to get a new edge list. So here we're matching on two hashtags, mutually tagging the same tweet. So hashtag 1, hashtag 2, where they both have tags relationship going to the same tweet. And then I'm also saying that the tweet cannot be a retweet or a reply to another tweet. So here I'm saying where not this tweet retweets or replies to another tweet. So that's in the not. So I'm saying that relationship cannot exist outgoing from this tweet. And this is just a trick to avoid matching on the same pair twice. So if Neo4j and Python, for example, are two hashtags that both tag the same tweet, they would be found once, twice. They'd be found when Neo4j is on the left and when Neo4j is on the right. And so this is just a way to get around them being matched on twice, because those are both valid patterns for this match clause, but we only are interested in getting that result once. And then I'm omitting Python because it's everywhere and it made my graph a little busy. So I'm saying that the Python hashtag cannot either be H1 or H2. H2 or H1 cannot be the Python hashtag. And then I'm returning the name of H1, the name of H2, and the count as weight to get an edge list that I can then pass to iGraphs tuple list. And again, this is not necessary. I need to remove this. This was a leftover code from when I was using the 3D graph thing. But anyway, so here we have a tuple list that we're passing to iGraphs tuple list, saying weights is true because we do have a weight column. And at this point, IG is now an iGraph graph object. And now we can do some algorithms. So let's say we want to do community detection among this subgraph of hashtags. So pretty easy in iGraph. It exposes a number of community detection algorithms, and they're all explained in the documentation pretty thoroughly. I chose to use community walk trap, which is it's really fast. It's a pretty fun algorithm where it essentially does a random walk around the graph and decides, which of the communities, because it keeps finding itself trapped inside of a cluster or a community. So that's why it's called walk trap. And then we're saying that we want to take the weights into account. Then we're getting the cluster membership essentially with as clustering. And it found 36 clusters among these hashtags. And here, just doing some busy work to get the data in the right format for visualization. So the Viz network, the Viz.js visualization that I've been using throughout, it expects a list of nodes and a list of edges where there's a unique ID and then there's a label that will display the text underneath the node. So here is just getting the group assignment for each node. So for each node in our graph, it was assigned a group with the community detection algorithm. So here I'm just iterating through each node, and I'm finding the group that that it's a member of right here, and then assigning that as a group key in this dictionary, this list of dictionaries. So now, in addition to the ID and label, we have which group it is in. And then for the edges list needs to be a list of dictionaries with a from key and a to key for each node. So AWS points to AZ, job points to Kelly jobs, and whatnot. Then at that point, you'll want to study. This will be included in the link to the GitHub repository, but you can study, what exactly is going on here. But essentially, it's just passing those lists, nodes and edges to Viz.js, and giving us a interactive visualization here within IPython. And here we see I have a bunch of hashtags tagging each other, and then the clustering algorithm determined which of them belong in their own cluster. And then, of course, if it ran out of colors, so these are definitely different communities, but it's going to be reusing some colors. If it's a disconnected component, it's in its own cluster. And then I wanted to find something to wrap this up with. That was pretty cool. It's right here. Cypher and Win. This is pretty much all you need to know about Cypher. And then I found the tweet that ended up making this happen. this tweet must have been caught when I was doing my scraping. Is learning images Cypher, but damn, it's pretty fast and pretty. So it had both Cypher and Win hashtags, and so that's what created this relationship in our subgraph. And then Cypher apparently, at least in the sample that I collected, wasn't connected to any other nodes. So that's all I have for these IPython notebooks, and just a getting started guide for all the different ways that you can integrate these analytics type packages with Neo4j, and then an example project of some real questions you might ask of a data set, and being able to then use what we learned in the Hello World code snippets and then apply it to a real data set.